Before we get too deep into our study of statics, we need to pin down what exactly we're talking about when we refer to a force. Forces are so fundamental to everything we do in engineering that it makes sense to spend a little time getting the details clear in our mind. Think about it for a minute. If a non-engineer came to you and asked you to tell them what a force was, what would you say? It actually takes a little bit of thinking to get the details clear in your mind. Fortunately for us, Isaac Newton did the hard work here and pretty much pinned down exactly what the fundamental characteristics of force actually are. Newton's three laws of motion are the foundation of modern mechanics and are a natural place to start. Newton's first law states that a body will remain at rest or continue moving with a constant velocity unless an unbalanced force acts on it. So if a ball is sitting stationary on the ground, happily minding its own business, it will remain that way unless it experiences a force, at which time it will start to accelerate in the same direction as the applied force. So far so good, this makes sense. When we kick a ball, it moves off in the direction that we kicked it. Similarly, if we imagine a ball moving in a vacuum, through space for example, it would continue moving at a constant speed in a particular direction unless an unbalanced force acts on it. The only reason that this doesn't happen on Earth is because the ball is subject to gravitational forces pulling it down to the ground and frictional forces slowing it down as it moves through the air. Okay, so we've established that a force will cause a mass to change its velocity. So is that the end of the story? Are we done? Well, not quite. There's a few more details to iron out. We know we can't simply pick a force out of the sky and hold it in our hands. So how do we know a force even exists if we can't pick it up or see it? We can feel forces, but if we didn't know forces existed in the first place, how would we know what we were feeling is actually a force? Well, the answer is in Newton's first law. If we observe a mass changing velocity, we know an unbalanced force has acted on the mass. Similarly, if we observe a mass with zero or constant velocity, we know that all forces acting on the mass are in balance. So the only way we know anything about a force is by observing its effect on mass. So we observe forces indirectly. So we've established that when a mass experiences an unbalanced force, its velocity will change. The relationship between force, mass and velocity is further clarified with Newton's second law, which states that the rate of change of velocity is proportional to the force causing it and always acts in the direction of the force. The first thing to point out here is the rate of change of velocity is simply another way of saying the acceleration, as acceleration is merely a measure of how much the velocity changes in a given period of time. Newton's second law basically tells us that the larger the force experienced by a mass, the greater the resulting acceleration of that mass. Newton's second law can be represented using one of the most famous equations in science. F unsurprisingly represents force, while dv/dt represents the rate of change of velocity, or acceleration. This is literally the change in velocity, dv, divided by the time it took to make that velocity change, dt. If we assume that the mass of an object under consideration is constant, we can see that the force applied to the mass is directly proportional to the acceleration of the mass. So with Newton's first two laws, we've got a good grasp on what force is and its relationship to mass and velocity. Newton's third and probably most well-known law tells us something about the relationship between forces. It states that for every action there is an equal and opposite reaction. We've all heard this one before. In the simplest terms, this means that as I stand on the ground, I exert a force on the ground equal to my mass multiplied by my acceleration due to gravity. Newton's third law tells us that the ground is exerting a reaction force back on me in return. The reaction force is equal in magnitude to the force I'm applying, and it's pointing in the opposite direction. So let's bring it all together. Think about this ball sitting on the ground not moving. Think for a minute and write down what forces are acting on the ball. Are there any forces acting on the ball? After all, it's not actually moving anywhere. Pause the video here if you like. Well, we know the ball has mass, and let's assume it's here on Earth. So we know it experiences a self-weight force equal to its mass multiplied by the acceleration due to gravity. Now this force must be balanced by another force, otherwise the ball wouldn't be stationary. It would be experiencing an acceleration downwards towards the Earth, exactly the same as if we dropped it from a height. So the ground it's sitting on must be exerting a reaction force, or equal in magnitude and opposite in direction, according to Newton's third law. Now imagine pushing the ball and thereby applying a force F. Newton's first law tells us that if F isn't balanced by another force, the ball will experience an acceleration in the direction of the force. Newton's second law tells us the harder we push, the faster the ball will accelerate. Okay, now we have a good grasp on what Newton's laws tell us about forces. We need to think about what information we need to know about a force in order to fully describe it. Think about it for a minute. If you needed to write down the key pieces of information about a force, what would that information be? In other words, what information must we know about a force to fully define it? Well, we'd like to know how big the force is, where the force is being applied, and what direction the force is being applied in. So if we imagine our force, all three pieces of information are necessary to completely define it. It could be argued that actually we only need magnitude and direction to define the force itself. But practically speaking, as engineers we want to know where the force is applied because this will obviously have an effect on how our structures respond to forces. On this basis we can see that force is actually a vector quantity, as it has both magnitude and direction, as opposed to say temperature, which can be completely described by a magnitude alone. As such, forces must obey the laws of vector addition. This makes our life a lot easier when it comes to analysing systems of forces. Now we're ready to consider 2D force systems. When multiple forces act at the same time, we refer to this as a force system. Coplanar forces are forces that lie in the same plane. Another way of thinking about this is, if I can draw the forces in question on a sheet of paper without any projection, in other words, the forces lie completely flat on the paper, then the forces are coplanar. If one of the forces in the system projects from the plane, my sheet of paper in this case, I no longer have a system of coplanar forces. The system of forces is three-dimensional. Fortunately, the majority of engineering problems can be simplified to 2 dimensions without too much loss of accuracy. So, in this course, we consider only 2D or coplanar force systems. Another term we need to be familiar with is line of action. A force's line of action is simply the straight line along which the force acts. It's a line of infinite length that simply extends from the front and rear of the arrow representing the force. If the line of action of 2 or more forces intersect at a common point, the forces are said to be concurrent. Consider some arbitrary 2D object. The coplanar forces applied to the edges of the object are concurrent because the lines of action of all three intersect at a single point. So can you think of a situation or an arrangement in which 2 coplanar forces would not be concurrent?